Thank you so much. I'm happy to speak for you, and I really wish that it was in real life and not virtually, and really hope that it will be back to normal at some moment. But better so than not at all. And I'm really enjoying this conference so far. Yesterday we heard a very interesting definition of understanding as classification. And that, of course, explains why the deep learning community spent first valuable years classifying cats and dogs. And I have for you on the right-hand side a picture of an animal, which can be a cat or maybe a dog or maybe something else. And if you would like, remind me, and in the end of the talk, I will tell you what it is, in fact. For me personally, it was very difficult here to decide what type of animal it is. And of course, on a serious note, we have to apply this for something which makes our world better, not just understanding cats and dogs. Some examples are, for example, in medicine, which is now very relevant, or in physics to suppress the background in experiments, or in applications related to social sciences. We want to, for example, control the sentiment of texts for various reasons, for example, removing the bias from texts, or in chatbots to understand what is this text about. So the applications for the classification algorithms are very many possible applications. And I written in the title, very deep learning. So the purpose of this talk is I want to explain what is meant by very deep learning, what are restrictions, and how the GPUs can help us here. People who know me a little bit, they know that I don't like very deep learning. I actually always tried to make a propaganda for less parameters and less layers and make it as simple as possible for the use case in mind. But there are also some cases where you need to go deeper. And for some example classification tasks, we can use machine learning methods starting from decision trees and so-called traditional machine learning up to the more modern deep learning. And for example, here on some real life data set where we had to classify texts which were labeled, it's a supervised task. And there we could clearly see that all the so-called traditional methods, also including the dense neural nets, were not performing as good as a convolutional neural network. It's not a big news, which we now found. It was just a test in our data that indeed all other methods couldn't crack the 94% accuracy in best case, and that was probably already in overfit, while the convolutional neural nets easily gives 98% without overfit. And that was for the first time found in 2012 already, when Krzyzewski and collaborators have won the competition for the classification of images, and for the first time introduced the convolutional neural networks and have proven that this method performed better than any traditional method, including the very popular engineering, where we first find some labels by engineering input data, analyze our data per hand, and then try to learn on the predefined labels. And so the deep learning was proven for the first time to work better than traditional methods in 2012. Was a classification task, and it was a convolutional network. On the right-hand side is a short mention what convolutional networks are, but I think people in this audience know it, and if not, you can later ask. So the idea in 2014, pretty soon after that came, why don't we go deeper? Means why don't we make the networks bigger, because then maybe we can fit the unknown function which describes our images better. As we heard yesterday in this book by Tony, is sometimes we just need more dimensions in order to define our class. And if we want to fit more dimensions, then of course we need to go deeper and have more parameters. So that is logical, and it's called the power of depth or the benefit of the depth. But there is a problem. That there are two problems. First is very obvious that if we have more parameters, we are easily falling into the overfit. But that was solved already in 2014, as I said, very soon after introduction of convolutional networks in principle, by Simonian and Gruppe. They introduced so-called very deep convolutional networks architecture, which managed to learn, for example, 54 layers without falling into the overfit. And that is, of course, already a great achievement. There was a problem that with 46 layers, the accuracy was less good than, for example, with 20 layers. So that you can see on the left plot. The important message is that the red curve is above yellow or brown, or whatever it's called, curve. So that shows that although, of course, with iterations we learn and get better, the network which is bigger and has more freedom to learn actually performs worse than the network which is smaller and simpler. So 56 layers, a lot of expensive computations didn't lead to a better accuracy. Moreover, it seems to saturate. So I cannot get better no matter how long I learn. So that is the second problem, and that is called in the AI communities the vanishing gradients problem, which means that basically you can understand it like that when you have many, many layers, by the back propagation, you need to transform the information in the end. Is my prediction correct? You have to transform it backwards in order to change the parameters in the very beginning. And when you have many layers, the information is lost by the time you got back. So the gradients vanished. And that problem for some time was very big and seemed to be unsolvable. In other understanding for the same problem, I would say you can think of it as a very multidimensional optimization problem, because when you have many layers, you have many parameters to fit. And then you have a hypersurface in an extremely multidimensional space. When you try to reach the global minimum in so many dimensions, necessarily your jumps will be too large and you will be trapped always in some other local minimum without possibility to reach the global one. And less layers, less parameters, less minima, less problems. So that fits until now with my philosophy, and I would say then forget about the very deep learning. 20 layers is already good enough until came the ResNet, and this is now the state of the art. So it was introduced in 2015 at the end of the year, and actually the modern version 2016, but I would say until now there was nothing better made. So the ResNet is the best architecture by accuracy for the understanding of images. Understanding of images is a standard task. Is when you see an image, you have to say a name for it, like picture of a woman, picture of a cat, is a painting of Rembrandt. Labels can be variously defined, but the idea is that it's a classification task for images. And you see that the solution, this ResNet, in the paper, the plot shows the right-hand side. Very important message that the red curve for ResNet, that's the very right plot, lies under the blue curve. So for the traditional convolutional network, 34 layers are not better than 18. Within error bars, I would say they're also not worse. So they did their best, but they're also not better. And on the right-hand side, you see that the conceptual problem of vanishing gradients was solved. because the 34 layers give a better performance than 18. At least I would say within 2 sigma. So, so this ResNet, what is it doing? How they managed? So first I show you on the left side one very, very simplified diagram of this architecture, which means on the left side is showing the traditional network, one part of it. So say like I arrive at this layer where I come in with an X. X doesn't have to be my input. It can be also output of a previous layer. And my layer transforms X into f of X. And then I go further. And the ResNet, this is called a block. It can be also 3 layers, usually not more than 3. It's a small normal convolutional network. And on the right-hand side of this scheme, there is a ResNet scheme. It was, by the way, in 2015-16, published by He and collaborators from Microsoft. So it has a so-called shortcut, which is shown here by this line around. And the meaning of the shortcut is the following. The output of this block is not the usual f of x, but it's f of x plus x. What is x? The x was, as I said, either input or the output of the previous block. And f of x is the usual transformation of this x. So why does it help us at all? So the idea is that if you make an output of this block, f of x plus x, it means that the x was not fitted. The x was already the input. And that means that what you have is a sum of changed parameters and not changed parameters. And I had to spend some time to understand it, and that's why I'm happy that I can do it for you now and a little bit explain. It is like I try to fit a complicated function with a lot of wiggles. And instead of trying to find a very large polynomial of very many degrees, in order to explain every possible wiggle, first I make an approximation with a relatively smooth function, which you can see on the right-hand side as an example. So I have a model with less parameters. It's just a short network. It is a very small block. And this block makes for me necessarily not a very detailed approximation, but a relatively smooth one. And then I look at the difference between this approximation and the actual function, which is f of x minus x. And this difference, the residue, which is plotted down, I now fit again with the next block, which I hang on top of this block. And the next block, again, is not a 54 layers, but it's only 3 layers. So it cannot make a very wiggly representation of this residue. It makes a necessarily a smooth representation. So I have a second smooth representation, which I add to the old one in order to make now approximation to the full function. And as I see, this one will also have a residue, and then making another block and another block, hopefully at some moment, I will have several functions, and the sum of them will give me the full function. This way, I can describe very detailed structures without having to fit simultaneously millions of parameters. But instead, I fit something like 1,000, 1,000, 1,000, 1,000, or 100, 100, 100. So it depends on the use case. And this helps to approach the global minimum consequently, also iteratively, without a danger of always jumping in and here, there, back, there, back, there, back. And this is the philosophical now explanation of the ResNet, which is, of course, you can find online the code and the schemes, but I find it very useful to think about what is actually happening. So then the people from Facebook, of course, ask themselves, is it making sense to apply this architecture also beyond the image recognition, also, for example, for the text analysis, because it's also a big question always with the artificial intelligence and deep learning. Do we generalize from one use case to the other. Is it possible? And that's also what I do for a living. I generalize from physics to text analysis and back. I find until now it works well. So they also found it in Facebook. And we also in the company analyze texts. For example, we always try to do something useful for our clients. So we can try to use the architecture of convolutional networks, and in particular ResNet, for predicting the click rates based on the title of the website. And this is in German, but the idea is that you can say the same thing in many ways. And we can, instead of experimenting, which is expensive, we can already by simulation predict which way is optimal. And then when our clients started using it, indeed we see that they have a better traffic on the website. So another application, classification of text, means we can also look at the emotional color of this text, sentiment. So in a very simple case, it will say if the person is angry or if it's a happy person, which is writing this text, is it a message which is hate or love? Or in this case, we looked if it's a message which is discriminating, or is it gender neutral and anti-biased? And that also helps our clients to be gender neutral, for example. And so where are the GPUs coming? So these use cases, which I just described, is about the websites, in particular career websites of the companies. For the web application, it is enough if the reaction time is below 1 second. And usually people take it, they find it okay, this reaction time. And so our task is always to lie below, let's say, half a second for our analysis, and then it's good enough. So I would say that in this case, our Python code to TensorFlow, even on CPUs, was performing fast enough. But now let's go to a use case where performance is very important. So where 1 second for one decision or half a second per decision is just very, very low, very large. So we are talking about now high energy physics experiment at CERN. In this particular collaboration is called NA61 Shine collaboration, where I participate. The event rate is of the order of 100 hertz. And in each event, we produce thousands of particles, and each particle leaves a track consisting of at least order of magnitude 10 hits. So the idea is that we have to analyze signal to background classification so fast that the decision can be done online in real time. Of course, it is impossible with one GPU, one CPU. We have a farm consisting of hundreds of nodes, but the limit is that we have to analyze a whole event, so all particles simultaneously, all tracks and all hits, within maximum 3 seconds per node. And if all nodes are fully working. So, and we don't want that also because we need a buffer. So that is a hard limit, 3 seconds. And so the question was, can we reach a very good accuracy for which we need a ResNet, a deep network, within only 3 seconds. And of course, we considered not only CPU clusters, but also GPU clusters for that. So the input data in this case is not images of cats, is not words of websites. It's, in this case, it's a readout from electronics in the so-called TPC, which is the main part of this detector. We have 4 bigger TPCs and some small. So which have more than 120,000 pads, and each pad records 200 something time slices. And so the input is such a 2-dimensional readout pattern where we have timestamps and pad numbers. So we look simultaneously at 11 neighboring pads and simultaneously at 21 timestamps, so that we can hopefully say if it's really a particle flying by or noise, because the noise can be up to 75%. of these hits, and it has to be removed before the further processing, so online. So it's described here some particular event which was measured, and so it's not a simulation. So we worked with real measured events. That's why we know that there is a large amount of electronics noise and some noise coming from the cosmic particles and so on. And since the upgraded experiment is still in build, we have a freedom to choose which electronics will be on which processing farm. That's why we could test on several CPUs and GPUs in order to find the good ones. So the labeling is important. So we have hits, as I say, in these TPCs. Here you see a picture of two big TPCs, and we have the left, this is the left and right one, the big ones. Then we have two smaller TPCs and some very vertex TPCs small. So, and on the left side, the gray picture is what we see in the measurement. And on the right side is a confusion matrix. So what we want is we want our algorithm to tell the yellow or orange left upper corner is the real signal, which we also identify as real signal. The right bottom corner is a real noise, which we hopefully identify as a real noise. But there is, of course, in real life, nothing is perfect. So sometimes there are false positives, which is something which is noise, but we identify as signal. And there is also false negatives, which is something we identified as noise, which is actual signal. And this is a lost signal. And we don't want to lose some important new particle. That's why we want to keep it as low as possible. So we want to reduce noise as much as possible, which means we need the green part of the confusion matrix as high as possible. And we want to lose as little signal as possible. So the red one has to be kept low. For this, also the performance is very important. And that's why we tested it on a typical CPU as the one which is probably going to be used, and a typical GPU, which is not the maybe most powerful, but the one which is realistic. And the results for the performance times I will show you after I will describe which networks we actually used. So first of all, of course, we applied ResNet, because we know from the previous studies on different use cases that this network gives the best accuracy. And so we hoped to reduce the noise in most reliable way and also without overfit. Indeed, we managed to have 92% accuracy, and approximately also it means we can look at the confusion matrix. So bad labeled as bad is the green. It's almost 90%. So we can remove 90% of noise. And the red is in this particular network is 5.5%. So, and that we can still tune, but order of magnitude 5%. So 5% of signal we lose, 90% of noise is removed. So the accuracy is good. And the question is the generalizability, for example, that we tested. Why? Because we have trained on one part of the detector, one of the TPCs, and then tested it on the measurements from the other part of the detector, other device, other TPC, which is standing 2 meters away and in a different magnetic field. And we have lost only 1%. So it means the validation is very good. So we can trust this 92, 91% accuracy. So our second exercise was we wanted to understand what was the reason for this good accuracy. Why the network was able to identify noise where physicists cannot by just looking at the signal. So, okay, maybe a very well-trained physicist can do it, but not so fast. And so we have exercised by building a 2-neuron network. It's extremely small, of course. It's not going to perform as well as a deep learning, but we already got 89% accuracy. So the idea was this network, if only 2 neurons already knows something. It can remove 87% of noise. Of course, it loses 8% of signal, but it's just an academic exercise so that we wanted to know what it bases its decision on. And then one of those students has built the weights of the network for all input parameters. And if you look at this three-dimensional plot, it's difficult to see, but we can rotate it. And then one can notice that in the center, the appearance of signal in the center of the actual center of the cluster is, of course, indicative that it's a real signal and not noise. That's logical. That's why the weights are positive. And off-center, it should be negative, but not in the corners. In the corners, it seems to be more or less around 0. So it's not important for the decision what is going on in the corners of this input data. Why is that? And we understood that it's because of causality, because the particles fly by, and of course they can hit several parts of the detector and leave traces in different paths, but not faster than light. And that's why we have a cross pattern here, where we see that the weights are negative of the peak if two paths fire exactly simultaneously with the same timestamp. It means the particle traveled faster than light, or if some particles suddenly stopped and started firing in the same path all the time, which is not possible because the particles fly with very high speed. So the network learned these very similar considerations, and already that leads to 87% of the accuracy. So we decided that we don't need the full ResNet, and we can concentrate on the full ResNet on the 2 dimensions, and we can concentrate only on this cross pattern of the input data. And then we have built an architecture which is tuned to these physics considerations. And I will show you why we did it, because of the performance, of course. So it's a convolutional network, but only built on the splitted input, which is on the cross pattern, and then combined for the decision without any more mixing the information from these two sides of the cross. So we call it splitted architecture. And the splitted architecture gives 92 also approximately % accuracy. It can remove even more noise than ResNet, 91%, and it loses 7% of the real. So, of course, it's not as big as ResNet. Now we can go to the main part. The main part is the performance, and does it really make sense to buy expensive GPUs? So, simple finals, the last network in the list, is very fast, but it's, of course, not performing with the demanded accuracy the collaboration needs. So then we can concentrate on the split architecture and ResNet. The split architecture gives higher noise reduction, has less parameters, but has a little bit higher false negatives. And the split architecture performs on CPU within the limit of 3 seconds, but on the border of it. But ResNet lies out of it. Prediction time is above 20 seconds per event, because event has a lot of actual individual decisions, and that is not usable by the collaboration. On the other hand, if we not run on CPUs, but on GPUs, then we suddenly see that the network ResNet, which has 100,000 parameters, it's gigantic, it can run within 1 second. And the simplest split network also needs 0.3 seconds. So it shows that such architectures of convolutional networks, and especially this ResNet, which is split in blocks, it is very, very effectively parallelizable on a GPU. So if I was making a decision, then I would say, let's not lose any data. Let's take the best architecture, which is ResNet, and buy some GPUs. So if we have 100 GPUs, we can do online analysis of this experiment. Now, of course, it's not my decision, it's the decision of the collaboration. This is first of all. And I don't want to sound only optimistic. Let's put a grain of salt. A grain of salt is that GPUs are producing a lot of heat. So they are needing more energy, and that's why 100 GPUs in one room, which has to be near the experiment, will just heat up, turn too much, and they say that is not safe for the electronics, it will just burn. So I am too much theorist to know all these details, but our task was to analyze different machine learning methods and different architectures, and to give all the information about the performance, about the possible noise reduction, possible speed and lost efficiency, the lost signal, and then the experimental collaboration as a whole can make a decision. We plan also, of course, to analyze which particular 5% of the data we lose, how this efficiency is depending on mass and momentum of these particles is very important in order to be able to compensate for this loss. And while this is in progress, when it's done, then it will be part of the actual run. And so I know it was a little bit heterogeneous presentation, but the main message I want to say is that deep and very deep learning is possible and useful, but has to be done with care. And if I want to use the best architectures, then I also need GPUs, because 100,000 parameters on a chip on a CPU will just take 20-something seconds per decision. So that is my message here. And I thank you very much for your attention. And I congratulate CPU Days with the 10th anniversary. Happy birthday, and many, many more to come.
Okay, thank you very much, Olena. It was a very interesting talk. And I found it very homogeneously from this perspective where we are.
Thank you.
From HEP and the GPUs. You immediately got a question from Gabor. Gabor, are you online? Okay, maybe I can read.
Can you read it, please?
Could you elaborate on how the causality appears in the DL structure?
Can you please repeat?
Could you elaborate on how the causality appears on the DL structure?
Okay, I understand. Yes, thank you. Very good question. Indeed, this causality, that was for me very amazing. So it's a very simple network, 2 neurons. And so input is 21 times 11 matrix of numbers. And so there's like 200 numbers, are entering 2 neurons. So we have like 400 numbers which are processed. And so we have then looked at all weights. The weights can be plotted on this 3-dimensional plot. And if a weight is positive, it means the network learned that this number, the bigger the number in this point in the matrix, the bigger the probability that it's signal. So that can be done online. There is such great service, weights and biases. It can feed hyperparameters and plot for you, for example, all your weights. But for the complicated network, we have so many millions of weights that this plot will not be understandable for a human, for me. And now as a human, I was trying to understand this plot, which seemed to have a structure. So this peak in the center. You mean how in this split network? Yeah, okay. So, but let me finish. So this peak in the center was expected. And the cross comes from the causality. And the split architecture, that's a different story. So the simple architecture learned causality just from looking at the examples. I didn't teach it explicitly. I didn't tell it, look, that the particle doesn't move too fast or it doesn't move too slow. The network just looked at the examples and noticed if something is too fast or too slow, then it's noise. And then for the split, we helped. We said, don't look at the corners. So we cut away the corners from our input and didn't even show it. So effectively, we just made a network which looks at the input from this band and from this band. And one arm of this split was analyzing only the dependence on the timestamp, and the other arm analyzed only the dependence on the pad number. So one was looking that not 2 pads fired simultaneously, and the other was looking that not one particle was always hitting the same pad. And we didn't tell it also to look at this particular functionality, it learned it also. But because we prepared the input in such a way by cutting important information, it could learn the causality by itself very good, and it had more parameters than a simple neuron. two neurons. It had more than 400 parameters. It had 4,000 parameters. That's why it could learn the causality even more detailed and even something additional to causality. So because it's a convolution also, it was combining the information from different paths together and from different time steps together. I don't know if it answers your question. Can you give me feedback, please?
I think I will do it, but maybe we can answer in the... Yeah.
Thank you.
Any further questions from Tony? Yeah.
So you have demonstrated how important the architecture is. Do you plan to do it somehow systematically to scan over all of the possible or reasonable architectures? Maybe, so you have shown three types and vastly different performance, so to say, in terms of number of parameters. So maybe I don't know. So how to proceed, how to explore this knowledge.
So thank you for your question. Yeah, actually, yes. This was a relatively short presentation of a work of 1 year in several centers. So in Frankfurt, and we have 2 centers in Poland, and in Gießen also my group a little bit helped. So the thing is that we, of course, tried much more architectures than I presented here. This is already a crystallization. So first step, although I, as a believer in deep learning, could say from beginning that convolutional will work better, but people tried dense networks, principal component analysis, normal decision trees, boosted decision trees, random decision trees, all possible decision trees, which are very, very fast. But my problem with decision trees, they overfit. They are just not generalizable. So we tried also pre-processing the data, so feature engineering also, of course. People tried first looking at what would be some interesting combination of inputs and then putting it in. So we tried many different things. And also what we did systematically, of course, the hyperparameters tuning was done systematically. And then we understood that if we want to tune on accuracy and want to have the highest noise reduction with the smallest loss of signal, then ResNet wins. And we don't need to go super deep, 3 blocks of 3 layers. That was enough. More didn't bring much and only made it slower. But ResNet is slow. So as I said, if we could just have enough GPUs and cool them, that's not maybe doable right now, but that would solve the problem. Then the next step was that the collaboration said, no, we need it faster and we need it cooler and maybe it should run on CPUs. And that's when we started thinking, wait a moment, do we really need 100,000 parameters? It seems to be stupid to just trust it, that it found a global minimum. And that's why we found the split architecture by looking at the limit of the biggest network, which works very well, and the smallest, these 2 neurons. And then we found this middle way. And I, from my side, formulated for the collaboration like this. These are the 3 best choices for you. Choose one. But behind the doors, we tried another hundreds. And maybe in the end, we will take the gradient boosted decision trees. Who knows? If we will understand that the efficiency. So the problem with decision trees is they don't generalize and they also lose more data. They lose maybe 12% of signal. But if we find out that these 12% are not the interesting ones, let's put it so, then it's okay. So that's the problems which people have in real life when we don't have infinite information.
Thank you.
Mm-hmm. Okay, thank you very much. Olena, one quick question from my side. So how could you improve the...
Sorry, it's echo.
Okay. So how could you improve the efficiency of the SHINE experiment at the moment? So I mean, can we see larger amount of higher statistic data soon or now?
Yeah. Yes. Thank you. So this is still going to take some time. So in simulations, of course, first of all, in simulations, we will see where we lose the data. And the noise approximately now is at the low energy of the collision. And argon-scandium small systems, there we have more noise in comparison because we have less signal. So there we have like up to 3/4 is noise. And if we remove 90% of it, that means we remove 76% of points which we need to combine into tracks. So you understand instantly that the speed up of tracking is by a factor of infinity. I tried to calculate this factor, my computer said it's infinity. So the combinatorics just improves so much that we will be maybe even able to do tracking online. And that is even necessary because after the upgrade, so approximately it was planned next year to start data taking if God helps with Corona and so on. So the idea is that the NA61 changed the electronics, readout electronics, and did other also upgrades, in particular forward detector. And so they will be able to run at much higher luminosities and much higher event rates than before. But that's only possible if on our side, also in the software side, we will be able to analyze it so fast. And a little bit of advertisement here. Let's say 1.5 years ago, it was not looking good. It was looking that with the traditional tracking, for example, and noise reduction calibration, the maximum speed up we could get, for example, is a factor of 10, and we needed this factor of 1,000. But now with machine learning, if we will convince that we understand the efficiency and so on, and we really use it, then it's done. It's realistic. We are under 3 seconds per event per node, and it's online. And so we can really do all the noise reduction and even maybe tracking online. So that's the holy grail is reached. I'm really optimistic. So I think in this case, the upgrade will work, and the NA61 will have a event rate approximately factor of 100 more than before. And we cannot now tell you, for example, that the omega C will be measured or not. It's too early